Okay. One thing I just forgot to mention. So, we are considering rotations, elementary rotations. So, suppose there is a vector x y and I move it to x prime y prime. So, this angle is theta. Then we can work out x prime y prime actually is, if you do not know how to work out, you call this angle alpha. So, this is alpha plus theta, length is p. So, this new x prime is p cosine within bracket theta plus alpha, and cosine theta plus alpha there will be a minus sign, isn't it? So, that is why if you work it out that way, it will be cosine theta then minus, in one of my earlier lectures I skipped this minus sign here, cos theta minus sin theta, this is important, cos theta minus sin theta and then sin theta cos theta. This I can write down because this is unitary. So, if I know one row from orthogonality I can find the other row. This times x y, that is c minus s c x y. But as I am following this book, you know, the theta that we consider typically is in the opposite direction, like there is a vector here, I need to rotate it so that this coincides with this axis. Equivalently, I am rotating this plane in the opposite direction. So, this theta is usually, I mean, this is a convention of theta. With that theta, cos theta will remain as it is, because cos theta, cos minus theta, they are same. Only this will become plus sin theta, this is minus sin theta, cos theta. So, our convention will be C s minus s c, and angle is in the clockwise direction, yes, clockwise direction, right. Just keep this in mind. Well, let us just go back to that what we are doing, that is we had x n m columns, okay, and we were minimizing this quantity epsilon square n as the norm square of this, you know very well. This is the usual norm, Euclidean norm, the sum of squares. Lambda has been pulled in here. This we are minimizing, and this was giving rise to, you know, E n, so it was giving rise to d n minus x n c n norm square, which is also equivalent to, if you take a unitary matrix Q n, if you choose an appropriate unitary matrix, square matrix, this is same as, this is what we did last time. Okay, and what did we do? Q n, just to Q this vector, this works on this, so that this resulting thing is equal to some upper triangular matrix and then zeros. Existence of such thing we have already proved, we have discussed using Gram-Schmidt orthogonalization and all that. So, that is always doable. R n will be a perfectly upper triangular matrix with non-zero diagonal entries, that is invertible if you have got Q n, if you have got this matrix having linearly independent columns. Okay, so Q n will be perfectly unitary and this will have non-zero diagonal entries and this will be invertible and all that. So, this into C n, and this vector we consider the upper half we give a name U n is m cross 1 and lower half whatever be the dimension this is what we gave, and therefore, this led to what optimal filter C cap n, that is we minimize it, that will simply if you take the upper half and solve this equation R n C n equal to this, because total norm square as you know will be norm square of this ln plus the upper part, isn't it, ln minus 0 from here, that is ln, and this minus R n C n. So, total norm square is the summation of is the norm sum of norm square of ln and norm square of this u n minus R n C n. Since R n is invertible, you can make and ln is independent of C n. So, only thing we can do is we can make u n minus R n C n equal to 0, that will be the minimum possible, and obviously that will give the best filter, best there is orthogonal projection, because projection is unique, and this minimizes norm means that will indeed corresponds to the orthogonal projection. So, you find out C cap n as R inverse n your u n. Of course, you do not have to compute R inverse n, R n is triangular, upper triangular. So, R n into C cap n equal to this you can easily solve by back substitution. One value you find out and then backward you can do it in clock, and that will give rise to array actually, pipeline manner. You can move it backward, back substitution. You find out and give it to somebody and take up the new data and solve, and that way that's. So, it will not really amount to a big computation, I mean big complexity and all that. We will see that. And your epsilon square n was simply this. Okay. And then we did how to obtain this q n. Okay, we suggested Gibbons notation and all. I am not getting into a recall of Gibbons notation. I hope you recall Gibbons notation, because that is quite graphic. Okay. Now, suppose we know q n minus 1, then how to get q n? We consider that also, that is first to develop q bar n minus 1 as zero transpose 0 vector 1. Okay. So, if you apply q bar n minus 1 on this guy, this will be what? You know this is nothing but lambda to the power half into delta isn't it? It is a diagonal matrix only, 1 square root lambda square of that square of that. So, if I take that 1 out, take out square root lambda separately, this is this, and this matrix times this means what? Upper half x n is what? X n is x n minus 1 followed by 1 row. Row consists of this x 1 n dot 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 x m n. So, if you do this into this, so this part multiplies this comes on top, and this comes as a row. On that this matrix. So, this q n minus 1 will work on lambda to the power half into this only. So, that will give rise to a upper triangular matrix and chunk of zeros. So, that means and multiplied by this. So, that will give rise to lambda to the power half r n minus 1, then zeros, this is m cross m, these zeros will be n minus 1 minus m into m, total is n, so up to this is n minus 1, out of which m gone, and this will be your u or x 1 row, isn't it? Now, I apply as I told Gibbons notation. So, actually you see q is never required. First understand that q is never required, it is required in analysis. If you give me r n minus 1, I simply form and give the new set of data. I have one slice, one row, whichever you stored them, and this r n minus 1, this lambda factor you bring in, and you have to do Gibbons notation. In the Gibbons notation, you have to find out those C S factors, because by Gibbons notation I will annihilate this will become 0, but the C and S factors I have to apply on the other elements, second column, third column, fourth column. So, those C S factors, but those C S factors are not difficult to be computed. Okay. So, first I annihilate this, I applied q a bar n minus 1 into this, I got this. and then I one Gibbons rotation. So, that this is 0 and first this matrix has only one entry here in the first and the last. So, just sum of the square of the two, square root of the square of this plus square of this, square of this plus square of this, square with the length, that will come here, this will be 0 and this will give us to one transformation for C and S appropriately. Apply that on the first row element and last row element of each column, each other column. So, this last row elements will get modified, first row elements will get modified. Then you consider the second column is diagonal entry, second entry, that and last one. There again you rotate, apply Gibbons rotation, so last one is annihilated, but that will not affect this 0 and this 0, because this 0 and this 0 is origin. You understand, that was the thing, na? That is, suppose you had one vector here, you rotate the plane so that your x is this corresponds to here, this has come back here suppose. Then if you this has come back here means only x coordinate, y z both 0, 0 0 0 0. There if you rotate the two, this is untouched and these are 0 0. So, if these are not both 0 0, things would have got changed, but since that is origin only, even if you rotate this plane, the origin does not get affected. Okay. It gets affected, you see, so in the first column this two zeros do not get affected, but other columns, third column, fourth column onwards, the second row entries and the last row entries do get affected, because they are not zeros. Do you see the difference? If you consider, if you are now annihilating, or maybe I consider an example. These are datas, huh? They are zeros. First, you had a data, you had data here. First, you are annihilating this. Length of this vector is coming here actually, and this fellow is getting altered. I do not mind. Next, you are considering this. You are annihilating this by appropriate Gibbons rotation. That will not affect this firstly, this first entries, because they are that, this axis will be untouched, that corresponding there will be 1 in the matrix, for this row there will be 1, this will not get affected, but second row and last row will get affected. But there comes the question, as far as the first column is concerned, there the second row and first row will not get, last row will not get affected, because this is already 0 0 means origin, isn't it? So, I am rotating this plane, say in this case y z plane, but in the case of first column no effect, because they are already 0 and 0. If you pre-multiply a matrix which targets second row element and last row element, in this case it will target 0 here, so result will be 0. Physically you are rotating this plane, origin remains at origin only. Okay. But that does not apply to the third, fourth other rows. There this fellow and this fellow will get altered, this fellow and this fellow will get altered, I do not mind. Please see this. Then again I consider this third guy and this last guy will be annihilated, that will not affect, that will affect, and then I apply the transformation. So, fourth column, fifth column, they are this this third row and last row, those elements will get affected, but not the zeros obtained in the first two by the same logic, so on and so forth. Okay. This Gibbons rotation thing we are doing sequentially. See the mode of operation, you are first, like you are doing here, suppose you are supposed targeting this first column first. What is the computation? You are finding out a few things. One, square of this plus square of this, the length of this vector. That is one computation you find out, because that will be the new coordinate here and 0 here we know. But apart from that, C and S you have to find out. C and S at least based by hypotenuse and sine, and what is that called, height by hypotenuse, that way you see S find. So, this is one computation. Once that is done, then you propagate C and S to this column, all these columns. So, that first and last guys are altered, all of them. This is one line of computation. Next time you consider this, again you do the same operation as you did here, same kind of processing, same length computation, same C and S computation, and then you propagate to the right hand side. That is the mode of, and as you do that, this guy which was handling this and computing the new length and C and S, it can take new column. If a new column comes or if something comes, it can do that. Anyway, I will come to that. I am just trying to show the computation flow. I will be detailed here after a while. Okay, this is the nature of computation. Okay, computations are very much similar. What you do for first column, similar operation do here and propagate the C and S. Third column also between these two, you target, find out the length. Using the length, you find out this, I mean this C and S and propagate. Okay. All right. So, apply this Gibbs rotations. So, that means your q n is nothing but q bar n minus 1 pre multiplied, you do that and then one rotation corresponding to the first column, you can call it G 1 n. G 1 n is a rotation matrix. There will be a C, there will be a S, there will be a minus S, there will be a C, and otherwise diagonal entries will be 1 and elsewhere zeros. A typical rotation matrix we discussed, and where C, where S, that will depend on which particular column you are, like in this case, I mean there are 4 boundaries C 0 0 0 S and last column row also minus S 0 0 0 C, otherwise it will be a diagonal matrix and so on and so forth. So, that is G 1 n, because I am making it dependent on n, my God. And then G m n. Physically, mind you, I am doing like this, but I am never interested in finding out q. No explicit computation of q n is necessary. It is necessary in our analysis, in our understanding. Computation does not need this. You gave me R n minus 1 and new data, I will rotate them by those computations. Okay. And mind you, q n I am not only applying on this, q n I am applying on this also, isn't it? Q n I am applying on these also. What is the effect here? Let us find out. This also have to find out. You are doing q n on this by that method. The previous R n minus 1 is given to you a new set of data, just rotate. No need to compute q n. So, say here also I have to do the same thing. What computation? Isn't it? So, q n again let us see. First q bar n minus 1 and this rotation matrices. Okay. Q bar n minus 1 times this. What is q bar n minus 1? Q bar n minus 1 is this. So, that working on this will be what? No? This lambda n to the power half, as I told you, we can always write like this. What is it? Is it this times d n and q n minus 1 before that. So, this working on d n minus 1 and 0 times the last. So, forget the last entry. This working on d n minus 1 on that q n minus 1 works. So, there will be q n, sorry, there will be q n minus 1. This one I forgot to write. There will be q n minus 1, yeah, q n minus 1, and this working on, very simple, this working on the last so d n. This actually, sorry, let me q n minus 1 working on No, just a minute. Let me write the correct expression. This is, I don't mind, I move on to a new page. This is your, let me write down step by step. So, this on that q n minus 1, this working on this lambda to the power half is a factor you take out first. So, this guy on this and q n minus on that, what will that be? That will be this vector u n minus 1 followed by L n minus 1. Are you not following this? What are the difference of u n and L n? If q n works on this vector, I take out the first upper m cross 1 point, I call it u n, lower part L n. If it is n minus 1, if it is n minus 1, if it is n minus 1, what is this? That is what it is. Honestly, lambda to the power half factor has to be brought in now. Isn't it? And the last guy d n. So, this part is your, because this is m cross m, this is m cross m, always m cross for any index. So, that means this is your L n, this is your this is not yet L n, sorry. I have done only this. I have to apply that Griffiths rotation thing. There is a final matrix. I am only applying q n minus 1, na? I am only applying this, but this is not q n. Q n has to be applied. So, let us this is not thing. Okay. But what is our q n? Q n is this is called T n, say, let us say sequence of rotations, and then that q bar thing. Okay. So, that means this vector now I have to find out, I can find out this is T n times this guy, T n times So, remember I am not bothered about q bar n minus 1, please see here also I am not bothered about q bar n minus 1 or q n and all that. I have to find out this. You gave me what is n minus 1, what is L n minus 1, that you gave me, like R n minus 1 you gave me this fellow, this fellow. What I have done, simply I have brought in the lambda factor and appended the new data for desired response at the bottom. From this side I am finding out those sequence of rotations, this side. Okay. I am triangularizing this data matrix. So, I know what they are, and the moment I know these things, this will be what? Just a rotation matrix, is it? One particular value will be C and S and correspondingly minus S and C. So, it will pick up just a pair of entries from this vector. From this vector, if you apply G 1 n on that, it will pick up a pair of entries. In fact, in the case of G 1 n, we know what it is, C 0 0 0 0 S identity matrix minus S 0 0 0 C. So, C on the first, C will work on the first guy, S on the last guy, and also that will come to the first position, remaining positions intact, and minus S times first guy, C times last guy, summation that will come in the last position. So, just this also will be rotated, this vector also will be rotated, is not it? By which rotation angles, that which came from the data side. So, it will be rotated once by this, then rotated once by this, rotated once by this, like that. So, I have to just do this rotation operations. No explicit computation of Qn is required. Okay. So, we will come to these computational things. Suppose consider m equal to 3, and now I also consider adaptive filtering problem, though it is not necessary here. M equal to 3. Okay, for the time being, we assume that we are carrying out with our initial assumption that our index of operation n is greater than equal to capital M. So, that there is no linear dependence problem. That I have to take care of, mind you, otherwise things are not complete. How to take care of those indices, those early indices where number of n was less than m, then QR does not exist, because number of columns is more than the dimension of the space. So, you cannot have a Q matrix. You understand that, na? So, how to take care of that case, that we will see, that is another story. But suppose our index n is way above that. In that case, I am just giving a partial idea of the computation, then again I will come to that initialization thing where n is less than m, and there I will consider adaptive filter problem, where these various columns of the data matrix will not be independent like x 1 n, x 2 n, x 3 n. It will be like what we did in the lattice case. First column, next will be Z inverse of that, next will be Z inverse 2 of that, Z inverse 3 of that way, which is a purely filtering problem. Okay, and pre-windowed case, that is 0, I mean first column as it is, then next one will have 0 followed by data, then 0 0 followed by data, that kind of structure we will assume. Okay, and remember that 0 0 structure is an upper triangular matrix, isn't it? That to make use of that, we will be using this. So, there is no direct relevance, but there is an upper triangular structure, we will make use of that. That is why the pre-windowed thing will be taken up. Just to give you an idea beforehand, there is a computation, Suppose this is a general case I am considering, but for the adaptive filter case we will be simplifying it. X 1 0. For the time being, let us assume our starting index is n equal to 1, not 0. Like in the lattice case, we started at n equal to 0 and went onwards. Suppose n equal to 1 is the starting index. Like that time I said initial condition at -1. Remember, in the lattice case I gave the values at -1. Here the initial conditions will be at 0. Okay. This book also does that, so I am just picked up from there. So, first by x 1 second dot x 1 n dot. This is a current index. What it will do? So, and do the business at current index, please. Do not go to the starting index, then that dependence independence will come up. Suppose this index is sufficiently large, we are doing it here. I am just giving a idea beforehand. This is not final. Also, this will not be final. There are some other linear section that I have to consider. I will consider tomorrow. Okay, but suppose it is so, it will always be CS things. I will consider m equal to 3 only, but otherwise I cannot draw an infinite array m equal to 3. What happens, this kind of round, this circle, this is one kind of processor, this is another kind of processor. This processor will compute, will take up that particular row where the 0, where data has to be annihilated, and therefore C and S are to be computed, like say first column. There you generate CS and then spread it to the remaining columns, remaining 2 columns. So, this will just do rotation, this will do computation. After that, you target second column, here we will have one more thing. We will see all this. It will become a triangle array here. This will propagate. Whatever I have here, this goes through. Same thing comes. Those who have done my course on VLSI for telecom, they know this. Sometimes the data propagates through processor. These are just broadcast, not broadcast, but they go through. Same C, same S is transmitted. You can, I will give the this function of these two processors separately. That is how you draw systolic arrays. You remember, if whatever processing unit you have, you draw it. Its function separately. You remember the DG and all that we used to do. Okay. It is not that formal way of doing systolic array, where you do a DG and the transformation. This is just directly using intuition intelligence. Okay. You did not do my course, so you won't understand. Should have done. That also was mathematical. Here it is D 1 dot 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 D n. So, remember this guy, since I have told it's the same processor use, same type of processor, what it will do? It will do some kind of C and S computation, will propagate them through this. Operations do not change, processor is same processor. This is not complete, there will be just one section for the triangularization, but this is not enough. But let us just see the computation thing. What these guys do? This guy does, I am drawing its action. Nah? It has some storage also. It is storing some value x. What is x? We will very soon see. And suppose it is taking, I will be using the x many times. Remember, the x is just related to this particular processor. Same x will not be, this x will not be, x will not mean the same thing in all. Okay, just you find the x here. Suppose it is u in, it will generate two quantities, C and S. How? So, let us do some kind of analysis now. It is like this, x and u in. What it will do? It will first compute x prime as what? This is the data, you have to multiply by that lambda thing. Na? This will be, suppose a triangle part was there. Okay. So, lambda to the power half into r n minus 1 and then this data, that is the situation. So, this is multiplied and then square added, length is found out. Firstly, you should check if you suppose this data is so happens the data is 0, then life is very simple. If this data is 0, it is already annihilated, is not it? Then your C should be 1, S should be 0, I suppose. Yes, C working on this and S working on this, C is 1, S is 0. Okay, you do not have to really go through all this computation in that case. In that case, your life is safe. I mean, you do not do so much of computation. You are following me or not? If this is 0, this can be 0 or non-zero. If it is 0, that is if, then obviously C equal to 1, S equal to 0. Is it? Yes, you rotate by 0 degree, cos theta 1 rotate by 0 degree. Just or otherwise, if you in the matrix form, just 1 times this, S times this, S times this, 1 times this, S is 0, 0 times this, 1 times this, you get 0 comes back here, this goes back here. Okay, that is a very simple case. When it is not, you find out x prime, this is a length, then in fact, let me say that you consider this instead of x, this goes for x, not x prime, this goes for x. Earlier it was x, x is to be replaced by this guy. Earlier in the location x was there, now x is to be replaced, but before that I am just saying this x. Now, but I will come to that later, just compute this, I will name it later. Look at x, certain things I did not say regarding rotation, that will come. Look at x. X could be, x is what? X could be here, say x corresponds to x axis and this corresponds to say z axis or say y axis. Other axes are 0 and we are not, they are not present here. Okay. If this is here and u here, this is a very simple case, theta in the opposite direction, isn't it? Theta in the opposite direction, C will be positive, S also will be C S minus S C, that S will be positive, cos theta minus sin theta, and that gave rise to that thing, na? Theta negative means it gave rise to, that is what it did in the beginning. So, S was coming to be positive, okay. That is the case, but it could be the other way also. And then what is the new value of the coordinate? Because the coordinate it will be rotated. So, this length itself with a positive sign will be the new value here. This is one possibility. Okay. That is, if x is positive, then either you are here or you could be here. If you are here or here, x is negative, we will consider that later. If x is positive, either here, so you rotate this way, or you are here, rotate this way. But in either case, this much length with a positive sign will be your x coordinate. You are rotating this way or this way, but this much length with a positive sign, right. So, that means if x is positive, then just this with a positive sign will be your new x coordinate. Okay. On the other hand, but what happens to S here? S, you are rotating in the opposite direction, into a positive theta counterclockwise. So, sin S will be minus then. When theta was this way, I had plus S coming. When theta this way, I will have minus S. Remember that. I am not targeting S at the moment, I am targeting C. On the other end, it could be here, and again I could be here or I could be here. If I am here, I rotate this way, but by how much angle? This angle only. And what is the x value? Negative, it comes out to be negative of that length. Square root is a thing, is a length, I find it is positive. So, I have to give a sign to that. The sign should be negative if x is. On the other hand, if it is here, even then I rotate, but sign remains negative. That means, new x prime will be, how to take the sign of x fellow? X by mod x, you all know this.
always taking it to the positive side. I mean, after it's just rotation.
This is convention. Will the analysis be different? I have to either this way or that way, because this comes in the mind first, na? This way.
No, sir. I mean, like you're saying for positive, you're ending up here. For negative, you're ending up there.
All cannot be positive.
No, what I'm saying.
No, what is saying this, instead of rotating this way, rotate it this way. That could be done. There is nothing, I'm sure, this is just a convention. There is, I mean, there is nothing fixed about this. Make no mistake, there is nothing fixed about it. But you have to follow a convention and stick to that. I am following the convention given by this guy, whose name is Hekin. So, okay, I am just following that. I am not ruling out those things. But the advantage, you know, this theta, cos or sine computation becomes then very simple. I am telling you why. If you just rotate only, because theta is always acute. If you just rotate by this much or this much or this much or this much, theta is acute. So, computation becomes, otherwise you have to consider a 180 plus theta or 180 minus theta, and all those things will come up. That is the thing. That is the thing. That is why you are very smart guys. You will understand more than what you understand here. So, these times so, what was earlier x, that will be replaced by this fellow. Now, C, now S. C is, if you are rotating this way or rotating this way, or if you are rotating this way or this way, C is always positive. Isn't it? Because C is cos. Isn't it? Our convention was this way, but even if the angle is in the opposite direction, cos of that is positive. Similarly, here counterclockwise, both are C is positive. Problem comes with S. S again both things, whether this is in this direction and this is positive or negative, or this is in this direction, this is positive or negative. S is more complicated. But again, you know, this straight trigonometry, elementary trigonometry, all of us, I mean, not me, but certainly you people are very smart on this. You know, so C will be what? Simply, I mean, don't bother about sine and all, just take the mod of the base, mod of the hypotenuse, the ratio, isn't it? Because C is always positive. So, that means C will be your mod x divided by this quantity. In fact, it is not just x, there is a lambda factor. Mod x divided by, you can take the mod of this or mod of same. This is your C. Remember, computation is in the processor, you need a squaring operation, you need a square root operation. These are the computations. Then people have done research, they have modified this, but I am not going into, where squaring operation or square root operations are not required by again mathematical, you know, I mean, tricks and all that. Okay, they simplified things. I mean, you can. So those are not beyond the scope of this course. You know, just giving an idea about keyword factorization based things is a very interesting thing. And especially when your number of input is very large, you know, suppose 1000, then these arrays, because otherwise if you have got 1000 line thing coming every moment of time, every needs so much of computation. But if it is systolic and pipelined, they will be all pipelined. That you all know. About that I will come. They will pipeline latches. They know very well. I mean, that you can apply cut set and latch and all that. That you know, isn't it? Or you have forgotten? Cut set retiming and all you know very well. So, I can just apply cut set here, cut set here, cut set here, cut set here. Resequence the inputs and all that. About them, I mean, to them I will tell. That's not difficult, because there is no feedback here, na? So cut set, or even if I don't use the term cut set, doesn't matter. Okay, which page was I? Here. Now comes the more difficult thing, that S. It was when I was considering this much, then a S was coming, and what was the S? Just sin theta. When angle was in the counterclockwise direction, it was just sin theta, S was coming, no minus S, and that S was this much by this much. When here, that is, if x is positive, this is also positive, then take the ratio of the I mean this by hypotenuse, that will be a sine. When this is negative, this is positive, then sin theta it is to base, it will be minus S, isn't it? So, that time you take the ratio of these two, minus will come. When here you have this is negative, this is positive, that time in the clockwise direction plus S will come, but when this is negative and this is negative, just a minute, I made a mistake. When this is negative and this is also this is positive, you are moving in this direction counterclockwise. So, minus S, if I make mistake please correct me, and the other way when both are negative in this direction plus S. So, you have to check the sign of both this part x part and that u in which is coming, u in is this along this axis. So, I am just giving you from the book, S should be let us see. This is x by this means if we x is in this direction, this is plus, in this direction minus simply. Okay. And in fact, I should take this ratio u mod u I, let us consider this mod u I n square by this, what will that be? This has the sign. So, mod, that is the mod magnitude, and if it is in this direction plus, if it is in this direction minus, that will come up here in this ratio. Okay. And this will be plus, if x is plus, this is minus, if x is minus. And this ratio mod u I n, forget about all sign, mod u n by hypotenuse, that will give that magnitude of the sign. And now you check, it will get this thing, that when both are positive or both are that and function kind of thing will come up, isn't it? X by, just you check, x by mod x, this can be either plus 1 or minus 1, and mod u I n, this mod u I n square you write as this, as mod u I n, mod u I n, and though this by u I n you write as this into u I n. So, this quantity is plus 1 plus minus 1, this quantity also x by mod x also plus minus 1. So, both the signs will be taken care of here as per Heikin.
So like there just un would have also worked.
Huh?
Only un would have also worked, right? I mean in the numerator, like instead of writing mod u square by un.
But you have to take the sign of u in, na?
Yes, sir. Just un.
Just u in.
In the numerator. That will take care of sign of u also.
Achha, okay. So, I will tell Heikin, it looks like. Anyway, this is pretty simple, otherwise, I mean, there is nothing conceptual here. So, C and S are computed. Okay, so, let us come back to this array. What this array is doing, mind you, this is not complete story. This is just part of that entire optimal computation, just that the diagonal matrix of the R matrix will come over here, that is the only thing I am saying. I need to complete this by tomorrow actually, it is not one day affair. So, C and S found out, you had that x 0 0 0, this is a upper triangular matrix given to you, and a new data has come up x 1 n and then x 2 n. What it did, this guy did, it annihilated this fellow, okay, replaced x by that x prime with the appropriate sign and all. So, this is here stored, because next time another data will come, next time another data will go, square of that x primes multiplied by lambda plus d square, next value x 1 n plus 1 square root, again same operation will be done. So, it is stored for use in the next clock cycle and still next clock cycle, all that. Okay. That is stored, and in our mind we know that this guy is 0. You do not have to do anything to implement that, this is 0. This we know in our computation. Only say new value, I am interested in the new R n. So, new value is known. Okay. And this C s goes to all these fellows. This guy, these people have, I mean, you know, they have their things stored. Like suppose this, forget about this to be x, suppose this you consider to be x. So, what it will do, this column gets C and S information, so it will find out C x. Okay. What will be the new thing? C x, C s and s times this one coordinate and minus s times this and c times this. Okay, lambda to the power half has to be there on this, lambda to the power half, because R n minus 1 into lambda to the power half. So, always a lambda to the power half is a multiplicating factor with all the elements here. Okay. That means, what it will do? It will replace this x by this is the processor I was writing. Let me just quickly complete this processor thing. Else x prime, this is just repetition of what I wrote. Saurabh, you tell me what you wanted. I am not thinking. I will just follow you. X by x prime into u in by x by mod x. Will that we do? Okay, I am not checking. I have no time for checking.
Actually, u n by x only should.
Both the signs are required.
This is u n by x.
No, I am not so sure.
This is fine.
This I am writing based on the input of this guy. So, tomorrow I will see. If this is wrong, I will have his marks deducted from mid-sem. Okay, this is that processor. The other thing is this processor. I have to define this processor. These processors, they take C, S, they take new data. New data means x to n. Say for this guy, x to n, there is the new data. Okay, say x I n. Here x to n, x 3 n, like that. Okay, x to n. And it knows this guy. So, what it will do? This will be replaced by x will be replaced by what? Sorry. And something comes out. What comes out? When something comes out, what comes out we call it say u out. Its purpose will be seen. And something goes in this direction. This is still T S, C, C, S, S. X I n comes in, u out goes out. Okay. What does it do? And it was storing some data x that will be modified by new x. What was that x? This fellow. Okay. that x will be replaced by, I am blindly writing from book now, that cannot help. X will be replaced by what? C times lambda to the power half x, isn't it? C times lambda to the power half x and s times this, s times this new fellow x I n, that will go for x here. And what will happen here? This guy will be called u out. In fact, we should call u out n, but I am just dropping the index. U out n is just minus s times lambda to the power half x I n plus c times, sorry, minus this is x plus c times. Okay. We will consider this in the next class tomorrow. Thank you very much.